Okay, so welcome everyone on day 6 of this online program. And our first speaker for today is Professor Pranav Parchit from ICTS TFR, and he will be speaking on duality in higher categories 1. And over to you, Pranav. Yeah, you can start now.
Thanks a lot, Surajit, for introduction. I also want to thank the organizers, Anita, Rekha, and Samik for this invitation to speak, and Suresh and Shrikant, the other lecturers in this program, for some interesting discussions leading up to the preparation for for putting together a coherent school here. That was great fun. So thanks everyone for inviting me. Yeah, so I have written out part of my lectures, and then I will be, just hang on, some technical issue here, okay. And then towards the end, I realized that the number of slides were getting to be too many. So let's see how much I get through for this lecture, and if there's time, I will then write out a little more live. Okay, so as Surajit mentioned, the title of my talk is Duality in Higher Categories. And one of the words there, duality, is a theme of the school. So the goal of the introductory lecture is to explain, what is duality, and why do we want to use, or why do we need higher categories to describe this, or why is it a useful framework to have higher category theory? So part of that will be to explain what higher category theory is, which other lecturers in this course have been doing from different points of view. Okay, so in today's lecture, what I want to do is first I want to fix, before I get to the real discussion on dualities, I want to fix some conventions on homotopical language, because that can lead potentially to a lot of confusion because of the differences in the different, there are different ways to talk about the same thing. So I want to fix that. And then I'll talk about, give a couple of examples of duality. And finally, I'll formulate the goal for this mini course, which is to describe a certain framework, a categorical framework for understanding dualities, for saying what a duality is and understanding, how to describe these dualities. Okay, so it's quite possible that I might only get through 1 and a little bit of 2 today, in which case I'll carry it over to the next lecture. Okay, so let's see. Yeah. So, so let's fix the conventions and the language we want to use. And by the way, please feel free to stop me at any point. This is supposed to be, I was told this should be directed at beginning graduate students and so on. So the goal here is not to get to something, there is no sort of big end goal. The goal is to prepare ourselves for the real workshop coming up later, which is got postponed due to COVID. So, so especially to the students, please feel free to ask questions. And maybe the moderator can ask me if I don't see the question in the chat box. So, so there are three main remarks I want to make about convention. The first is that we're going to work throughout homotopy theoretically. Okay, so even though I'll be talking about some algebraic structures, we're going to work homotopy theoretically. Another way to say that is that everything in sight is derived. So I want to explain what that means, at least in some heuristic way. I can't explain it in all its technical detail, but I'm going to explain what I mean by working homotopy theoretically. The second is that I'll be working model independently. So when you work with homotopy theoretic objects, there is always some, because we work with set theory as the foundations for mathematics and not some homotopical foundations, you have to specify some point set theoretic model for the thing that you're working with. But it turns out there are many different models for the same thing. So you've already seen that when you talk about topological spaces and simplicial sets as both modeling the same thing. They both model the same homotopy theory. Or in Somnath's talks, you saw that you can model rational homotopy theory using certain types of objects, algebraic objects called commutative differential graded algebras. That's one model for rational homotopy theory. There are other models like DG Lie algebras and so on. So there are often different models for the same homotopy theory. So after I explain what I mean by homotopy theory, I want to make a convention that all the results I will talk about will be model independent. So I won't specify the set theoretical models. If you have some question about how to make things rigorous, how to provide one particular set theoretical model, you can ask me and I can direct you to a reference. But the idea is that it's not that important to, it's like if I want to talk about the theory of groups, if every, then, well, in principle, you should specify what model for set theory you use. You work with Zermelo-Fraenkel set theory or Gödel-Bernays theory or something. And then you build up, and then you say, okay, I have a model for the theory of groups in this language, in the language of set theory. Once you do that once and for all, you know there exists a model for the theory of groups. And you can study the theory of groups without specific, every time talking about Zermelo-Fraenkel set theory. You can also model the theory of groups using category theory as a foundation for mathematics. So the point is that there are various things, artifacts of dealing with a particular model that are not really relevant for understanding homotopy theory. They're sort of foundations that someone needs to work out, which are often hard to work out. But once they're worked out, you know that there's one model and there could be many other models, and you can choose whichever one you want and work with it. But the things you want to talk about are not the sort of details about these models, but really about things that are intrinsically homotopy theoretic. So that's what model independence means, and I'll explain in a bit more detail what I mean by that. And the other thing is that the final point is that I'm going to work from a perspective where I view algebra as sitting inside higher algebra, or equivalently, we will be viewing ordinary rings and modules as discrete ring spectra, or as discrete DG rings, if you like, as DG rings which have no cohomology outside degree 0. So all of ordinary algebra you can view as sitting inside this homotopical algebra. And now that you've seen Samik's lectures on spectra and Shrikant's lectures on DG rings and so on DG modules, at least these objects on the right-hand side should be familiar to you. And so I'm going to implicitly be viewing ordinary rings and ordinary modules as sitting inside there. Okay? There was a brief discussion at the end of yesterday's lecture about this, and it's a perfectly valid thing to do if you're working homotopy theoretically. So up to homotopy, it all makes sense. So I'll try and elaborate a little bit on these points, hopefully. Let's see how much. It's a 45-minute talk, so I'll do my best. Okay, so let's see. Let's go to the next slide. Okay, so where was I? Oh, sorry, I didn't need to go to the next slide. Right here. So first, let's begin with what a homotopy theory is. Okay, so by homotopy theory, I can mean any one of the following things. So the first option is I could mean a category, an ordinary category, equipped with a subcategory W, which we call weak equivalences. Such an object I'll call a relative category, a pair like this. And that's an example of what a homotopy theory is. Now, there's one way to say what a homotopy theory is. You've already seen examples of this. You could take C to be topological spaces and W to be weak homotopy equivalences. You could take C to be chain complexes over some ring, and you can take W to be quasi-isomorphisms, and so on. Right? So there are many, many examples that you can construct of this kind of thing. And morally, you want to sort of invert the weak equivalences. That's what Rekha was talking about. You want to declare these weak equivalences to be, to be actual equivalences, to have inverses up to homotopy in some. The second option is I could mean by homotopy theory is a category C enriched in topological spaces or simplicial sets, or some suitable notion, or some suitable model for what a homotopy type is. Okay, so I could mean a category enriched in top or simplicial sets. So what does that mean? That means that for every pair of objects, I have a space of maps, not just a set of maps, and that could live in top or S set depending on how I choose to work with it. It could also mean, a homotopy theory could also mean a quasi-category, which I think is something that Rekha will talk about later in this series of lectures. It could mean a complete Siegel space, which is something I hope to introduce towards the end of the lecture series, or maybe in the third lecture, possibly, or etc. So there are several other models for what a homotopy theory is, or equivalently what an infinity of one category is. And I could mean any of these things. The whole point is that you shouldn't be too tied down to which one I'm talking about, right? So in any example, I'll be dealing with one. It turns out that all these are equivalent notions. To say what is equivalent, you have to talk about a homotopy theory of homotopy theories, and then say that the homotopy theory of relative categories is equivalent to the homotopy theory of simplicial categories, is equivalent to the homotopy theory of quasi-categories, and so on. So there's a very deep theorem that says that all of these are equivalent. Not only are they equivalent as homotopy theories, but they're equivalent in a very strong sense. Namely, that there's only one thing one automorphism of the homotopy theory of homotopy theories, for example, the homotopy theory of relative categories, which is the automorphism which reverses the direction of arrows. So you take a category to its opposite. So these equivalences between 1 and 2, 2 and 3, and so on, are determined up to this ambiguity of replacing a category with its opposite. So it's a very strong notion of being equivalent. Okay, so I'm not just saying there is some equivalence between these two. I'm saying there's some equivalence up to a Z mod 2Z ambiguity. That's the only ambiguity. So they're really equivalent in a very strong sense. Now, the first two definitions are not really the best definitions to work with homotopy theories. They're just the easiest definitions to write down and the easiest definitions to give examples of. That's why I wrote them down first. It's actually much more convenient to work with something like definition 3 or definition 4 or some of the other definitions that exist. But I'm just using this because it's convenient for this lecture series. Okay. So now let me tell you how to go between two of these things. So the first model was relative categories, category with a weak equivalence, with a notion of weak equivalences. And the second notion was a category enriched in simplicial sets. And I want to describe a construction which takes you from a relative category to a category enriched in simplicial sets. So this thing is called the Dwyer-kam simplicial localization. And it's characterized by a universal property. So from CW, it produces this simplicial category LW of C, together with a functor from C to LW of C, which has the following universal property that for any functor from C, C is just an ordinary category here, to, I shouldn't have put an H over there. There's no H. Let's see, there should be no H here. For any functor from C to X, where X is any simplicial category, with the property that for every element W, for every weak equivalence in C, I should have said for every W in, sorry, I apologize, this should be W in W. Right? So if I take any weak equivalence in C, it should get mapped to something in X, which is invertible up to homotopy. Now, what do I mean by invertible up to homotopy? I mean that it's invertible in this category HX that you can construct, where HX is an ordinary category whose objects are the same as the objects of X, and whose set of homomorphisms between two objects is the connected components of the mapping space in script X. Okay. So explicitly, this means that f of W has, given f of W, given W, there is a morphism G in X, such that G composed with f of W is homotopic to the identity, and f the other way around as well. F of W composed with G is homotopic to the identity. Right? So given any such f, there should exist a unique factorization over here from LW of C to X. So this is a universal property. You can ask, does there exist a category that satisfies, a simplicial category that satisfies this universal property? And it's a theorem of Dwyer and Kam that there does, and it's called the simplicial localization. So you can ask for a more explicit description, a more explicit model for what LW of C is, instead of just, I mean, I haven't given you any model. I've just told you that it exists. And in fact, here's an explicit model that helps you understand what this thing really is. So let's take two objects, X and Y, and let's ask, this thing is called the hammock localization. It's an explicit model for the simplicial localization, also due to Dwyer and Kam. So this hammock localization is a simplicial category. So for any two objects, X and Y, there's a mapping space, and I want to describe the k-simplices in this mapping space. Okay? So the k-simplices are going to be represented by diagrams of this form. So let's just stare at this diagram for a second. I have an X on the left, a Y on the right. Okay? And I have, the columns have length k. Okay? So in the simplest case, I'm looking at 0 simplices. So the columns have length 0, and I just have one string stretching from X to Y. And what is the string? The string is a string of arrows, some pointing forward, some pointing backwards. And the rule is that the backward arrows, which have the tilde on top of it, are all weak equivalences. Okay. So what have I done? I've formally inverted elements of W. So I have a zigzag. So I'm allowed to draw them backwards because they have inverses. So when I formally invert elements of W, I get a zigzag of arrows like this. So each morphism in pi0 of map xy is represented by such a zigzag, of course, there will be an equivalence relation on the zigzags. So the equivalence classes of such zigzags will be the actual morphisms. Okay, so there's an equivalence relation on them. Now, similarly, what are K simplices? K simplices are zigzags arranged in rows, in K rows, with the vertical arrows here being weak equivalences, such that all the squares commute. Okay? So you can describe these as K simplices as being the K simplices in the nerve of a certain category, which I won't get into. But anyway, so here's a very explicit model, and it also tells you, it's very close to the definition, right? You're trying to invert elements of W, so you invert them, and the natural thing to write down are these zigzags, because you can elements in W are allowed to go backwards. But then you also want to say that certain zigzags can be identified, and they're identified by a path. The path is given by the vertical arrows, and those are in W. Anyway, so you can. I'm not giving you enough detail to do much with this, but you can. This is just to say that there is a very explicit model, and you can go read about it if you're interested. Okay. So yeah. So now I just want to say, so that was what I meant by homotopy theory. Now, what do I mean by working homotopy theoretically? Because I will always be working homotopy theoretically, but I won't specify it very explicitly. It'll be implicit. So let me just say what this means. So the slogan here is that equality is a bad notion, in quotes, that you should always remember an isomorphism, the isomorphism you specify between two things, any two objects you work with. You shouldn't say they're equal. You should specify how they are equal. If you're a topologist or a homotopy theorist, one way to think of this is to say that I specify a path between any two objects that I want to declare to be equivalent, right? So that equivalence must be witnessed by a path, and there could be more than one path that witnesses an equivalence between two objects. And those two paths need not be themselves equivalent. They may not be homotopic to each other. So there can be multiple ways of identifying two objects, and this is central to homotopy theory. So the idea here, you can describe the slogan in two ways, that you always remember these isomorphisms, and everywhere in sight, throughout all your calculations and everything, you replace sets by spaces, and you pass to the connected components only in the final step when you want to get a number or some answer out of your problem. Okay? So that's the slogan, what it means to work homotopy theoretically. So, okay, this might sound, if you haven't seen this before, this might sound like some abstract principle. What does it mean in practice? So let me illustrate this through an example. I think that's the best way to understand what is going on. Yeah, I think there's a question.
Yeah.
Was there a question?
There are two questions in your chat, but I think it is already answered.
Okay. So let me give you an example to illustrate what it means to work homotopy theoretically. So let's work in the category of base spaces. Okay, so spaces, it could mean whatever notion of spaces you like. If you want to be concrete, fixed topological spaces, and I'm going to work with base spaces. Now, so my base point is given by x. Now I can ask, what is the pullback of this diagram? I have a diagram point mapping to x and point mapping to x. And of course, there's the naive pullback, which is just a point, right? Because a point in the fiber product is just a pair consisting of a point up here, and which map to the same point down in x. And this point maps to x, this point maps to x, so there's exactly one choice here. So that's a pullback diagram. Pretty boring. But there's a problem with this this definition, that it's not homotopy invariant. What does that mean? That if I can have a weak equivalence of diagrams between this diagram, the one I was considering, and another diagram, where I replace the point here by the path space, all paths which start at x, at our base point x. Right? It's a based path space, if you like. These are base spaces, so I'm basing the interval at 0, and then I'm looking at the based path space. So the path space contracts onto a point, so it's contractible. So it's weakly equivalent to a point. So this is a level-wise weak equivalence of diagrams. And we just saw the pullback of the first diagram is just a point. I can ask, what's the pullback of this diagram? And of course, if you just naively compute the pullback, it's just the loop space of x based at this base point, right? Because it's a set of paths starting at x whose endpoint is also equal to x. Because this projection is taking the endpoint. So maybe I should write that. So maybe I should write, this is gamma goes to gamma of 1. So it's not homotopy invariant. And that's because we didn't think homotopy theoretically. In the definition of the naive pullback, let's just go to, maybe I should go to the next slide. In the definition of the naive pullback, if I have some diagram,
can I ask something?
Y mapping to, yeah, go ahead.
So in the beginning, you were assuming C to be some kind of a category enriched in some simplicial sets or Kahn complexes or something?
No, I didn't. I said there were many different ways I could talk about homotopy theory. One of the ways is that C is a category enriched in simplicial sets or simplicial spaces. The other way is relative categories.
Yeah, that's true. I think you somewhere between talked about mapping spaces. So I thought it was like Kahn enriched maybe, or like.
No, right now, maybe are you asking me what I'm doing right now at this moment?
No, not right now. One slide before, like there was,
over here?
I think, yeah, while talk.
Which slide? This one?
Yeah, here. Yeah, you were talking about pi naught of mapping spaces and stuff. So I thought you were talking about enriched category of map.
Like yeah, you're right. So what I'm doing here is I'm constructing from every relative category,
right,
which is just an ordinary one category with a set of weak equivalences. I'm constructing a category enriched in simplicial sets.
Okay, but the category in itself is not enriched, you're saying?
Over here, it's not. This is just an ordinary category with a set of weak equivalences, with a subcategory of weak equivalences.
Oh, okay. Your localization mapping space, because of this constraints, become a simplicial. Yeah, okay, I see what.
The whole point is that I'm starting with a one categorical piece of data, which is a pair consisting of a category and a subcategory of weak equivalences. And I'm producing an enriched category from it.
Okay, thank you.
Category enriched in spaces. It turns out you can also apply this simplicial localization to a category that's already simplicially enriched.
Right.
You can do that. So you can start with C already being simplicially enriched and take W to be some subcategory of equivalences and invert it. And this universal property does hold. So that is true, but I'm not considering that more general setting because I'm trying to explain how to start with an ordinary category and an ordinary subcategory of weak equivalences, one category, and produce from it a category enriched in spaces.
Yeah, sorry, I thought it was enriched already, but it happened after localization, it's enriched. Thank you.
Yeah, so if just going back one slide, I'm trying to explain the relation between the first model for homotopy theory and the second model for homotopy theory.
Yeah, thank you.
Right, and I'm saying that, okay, so once we know that these two, there's a way to go between these two, we can freely go between one and the other. Sometimes we can talk about a category with weak equivalences. Some other times we can talk about a category enriched in Kahn complexes or whatever you like. And some other time we can just talk about quasi-categories. We don't have to be very careful as long as we know which statements are model independent, which are true in any model, which are intrinsic to infinity category theory.
Thank you.
I mean, the key point is, of course, knowing what is model independent. So for example, let's just go back to ordinary, I think this is an important point. So let's just go back to ordinary homotopy theory. Let's forget about infinity categories and all that. So if I just take topological spaces, I can have different models for the same homotopy type. For example, the real line is homotopy equivalent to a point. I can ask what properties of a topological space are truly homotopical, are model independent of which model I picked for this homotopy type. Now, if I took a property like the number of points, the cardinality of the set of points, that's not homotopy invariant because the real line is uncountable and a single point is just one point, right? So we should understand first what things are sort of not dependent on models, and then we can freely talk about it without having to every time specify the details about the models. That's the whole point.
Yeah.
Did that answer your question?
Yeah, it answers. Yeah.
Okay, so let me just see, where was I? Right. So now what was wrong with the way we constructed the pullback? The problem was that in the naive pullback, if I have a diagram like this, y maps to x, z maps to x, and I take the naive pullback, then I'm looking at a point y and y, a point z and z, such that f of y is equal to g of z. And we said that equality is not a good notion in homotopy theory. We don't want to declare two things to be equal. We want to specify how they are equal. So a better thing to do is to say, I take define this thing called the homotopy pullback, where a point in the homotopy pullback is a point in y, a point in z, and a path gamma identifying f of y with g of z. So if you like, here's a definition of a homotopy pullback. Now, one thing to note is that the square is no longer a commutative square in the usual sense. It's what's called a homotopy coherent square or a homotopy commutative square, which means that if I go around the top, f composed with whatever this horizontal map is, and if that's not equal to going around the bottom, but there's a homotopy connecting going around the top to going around the bottom. So f composed with alpha here is homotopic to g composed with beta here. And that homotopy is part of the data. That's what's important. It's not just it's not something that exists, but it's something that we specify. So just as ordinary pullbacks classify, the ordinary pullback diagram is sort of the final commutative square in the sense that every other commutative square will map to this one. The homotopy pullback square is the homotopy final homotopy coherent square. Okay? So basically all you have to remember is that you should always never say two things are equal, just remember how things are identified. Just follow that principle to its end, and you will always end up with the right construction. So a sub-example of this definition of homotopy fiber product is this loop space that I talked about. So without talking about the path space, let me just sort of directly get it from this definition. The homotopy fiber product of point and point in X is the set of tuples point, point, and a path gamma from the point to itself, from gamma of that, from X to itself, which is exactly the loop space. Okay. So it comes directly out of the principle that you don't declare two things to be equal. Now, if you're getting bored for the rest of the talk, here's a fun exercise, which will be important later when we talk about Hochschild homology. It's a very important thing in algebra, which maybe some others might also talk about. I'm not sure if Shrikant is planning to talk about it, which is to show that this is a push-out square. You start with this very boring data of just points, 2 points mapping to a point and 2 points mapping to a point, and take the homotopy push-out. Convince yourself, without any technology, just using this language that I said, that equality is bad, so you always remember how you identified things. Just using that, try to convince yourself that this is a homotopy push-out square. Right? So first of all, it can't be a commutative square. It's going to be homotopy commutative, and convince yourself that it's in fact a homotopy push-out square. It has universal property. Okay. So next, I just want to make a remark. So actually, all these are just preliminary remarks, and from the way time is going, it doesn't look like I might finish everything I wanted, but let's just do what we can. So where do model categories fit into this whole story? So you've heard about model categories, so I thought I should make a connection to what other people have already talked about. So a model category is nothing but a relative category with some extra structure, right? The extra structure are cofibrations and fibrations. That's what you saw in Rekha's talk. And you also saw this in disguise in Suresh's talks and also Shrikant's talks, where in Suresh's talks, the cofibrations and fibrations appear when you take injective and projective resolutions and so on. So those are also examples of cofibration and fibration. Now, the point I want to emphasize is that this extra structure, the cofibrations and fibrations, they are not intrinsic to the homotopy theory. Okay. So you shouldn't think of them as part of the homotopy theory. They're something that we use to do computations. So here's an analogy. Choosing a model structure given an underlying pair CW is like choosing coordinates on a fixed underlying manifold M. If I fix a manifold, I can abstractly study the manifold and do everything I want on it. But if I want to do a calculation, it might be useful to choose a particular coordinate system. Okay, so this analogy, I think, is due to Bertrand Cohen. But yeah, anyway, it's just an analogy. So maybe it doesn't matter if I attributed it correctly or wrong. But that's a useful way to think about it. So in a certain sense, model categories are very useful in the same way that coordinates are useful. But in another way, we don't want to get too hung up on which model structure we're using or something, as long as it does the job that the calculation that we want to do. Okay, so it's a tool for computations. So what kind of computations? Maybe I can just make a couple of remarks, which will help, I think, to place this in a bit of context. So on slide 5, let's go to 6. Sorry. So what are some examples of computations? So one thing you might want to compute is the mapping space between two objects. So at the simplest level, I might want to compute the mapping space in the homotopy category of C, where C is some simplicially enriched category. Oh, sorry, not some simplicially enriched category. I'm talking about, oops, sorry, I think I should write H of LWC. H of LWC. Or H of, or HOM in CW inverse. It's the same thing. So maybe I say HOM in CW inverse. And I just want to remark that I said earlier, which I wrote it, but I didn't say it. So let me just go back. That when you do this simplicial localization, you can form this H of the simplicial localization, which is taking pi naught of the mapping spaces. And what is that? That is something familiar. H of the simplicial localization is nothing but CW inverse, right? Inverting weak equivalences. I think I said this in words when I talked about the hammock localization, but I just want to emphasize this point. Okay. So we might want to compute HOM in this H of the simplicial localization. And that can be computed more effectively instead of using these hammocks and so on, which are not very easy to compute with because you're working with some zigzags and you don't have control over which objects can occur in that zigzag and so on. So if you want to control that, you can put a model structure and you can hope that there is a model structure on your relative category. And then you can compute this HOM in CW inverse as HOM in C from a cofibrant replacement of X to a fibrant replacement of Y, divided out by the relation of homotopy that Rekha talked about. In fact, you can do better. Namely, this HOM is nothing but pi naught of HOM in the simplicial localization. And you can ask, can I actually compute this mapping space in the simplicial localization in some effective way? And it turns out that you can use what are called co-simplicial and simplicial resolutions in a model category using the extra structure of fibrations and cofibrations to compute this mapping space. So that's one thing that the model structure is useful for. The other thing that the model structure is useful for is for computing things like homotopy limits and colimits. Okay? And homotopy limits and colimits are examples of derived functors. So you can, more generally, you can compute derived functors using model structures. So what are derived functors? Sometimes a functor between two relative categories, category with weak equivalences to another category with weak equivalences, may not preserve the weak equivalences. We saw an example of that. We took the category of diagrams of this L shape, and we took the limit functor. The limit functor didn't preserve weak equivalences. And so we had to derive it, do something to it, to make a functor that preserves weak equivalences, which is what we call the homotopy pullback. So more generally, there are various functors that don't preserve weak equivalences. And to compute, you can try to approximate them by functors that do preserve weak equivalences. And that's what derived functors are. And you saw that in Suresh's lectures, where you take, for example, sheaves on a space and you take the global sections functor, and that doesn't preserve weak equivalences between chain complexes of sheaves, but the derived functor of global sections does, and that's what you call sheaf cohomology. Right? So sheaf cohomology is a name for the derived functor of global sections, but there are lots of derived functors you might want to compute, and the way you compute them is by taking cofibrant and fibrant resolutions and then applying the original functor to those resolutions. So instead of doing the general theory, let me just show you an example of how this might work. So let's go back to our pullback diagram. So we start with this pullback, this candidate for this diagram of which we want to form the pullback, and we want to compute the homotopy pullback. So here's what we do in this particular case. It doesn't work for more complicated diagrams, you have to be careful. You replace Y to X by a weakly equivalent fibration. And then you compute the naive pullback of this new map. It turns out, you can prove a theorem, if you like. It's a theorem or a definition depending on how you do things. I prefer to call this a theorem. This naive pullback of this fibrant replacement with Y replaced by the fibrant replacement here is the homotopy pullback. So it's a way to compute the homotopy pullback. So we saw an example of this where we replaced point mapping to X by this fibration of the path space mapping to X. And the naive pullback of the path space mapping to X was the loop space of X, which is the correct homotopy pullback. So it's a computational tool. In this case, it's a computational tool for computing homotopy limits. Where am I? Did I finish today? Where did I go? Page 7. Okay, not bad. I think I'm doing okay here. All right. So just for the future, because I might want to use the word infinity category at some point, and also to make connection with Rekha's later talk, infinity category is a name for homotopy theory, for a homotopy theory in the sense I described it. So what do I mean by model independence? So the other convention is going to be model independence, which I think is again of independent interest to talk about this. So I said what it means to work homotopy theoretically. Now I just want to again emphasize one aspect of this, which is model independence. So model independence will mean the following, that we don't, so for example, it will mean the following, that we will suppress the model that we use for the homotopy theory of spaces. Here are a bunch of models. I could take topological spaces with weak equivalences. I could take simplicial sets with weak equivalences of simplicial sets. But those are not the only two models which are equivalent. There are other things. For example, simplicial sets are pre-sheaves on delta. I mean, they're functors from delta up to set. You can replace delta by certain other categories, like the category theta, for example, which I'm not going to talk about, which is just one of a whole family of categories on which you can look at pre-sheaves of sets, and those form models for homotopy theory. Okay, so Grothendieck initiated this whole program to understand which categories you can replace delta by, and such that pre-sheaves on them will give you a good model for homotopy theory of spaces. And there's a whole bunch of them you can work with. So I won't say that I'm working with spaces, simplicial sets, etc. Similarly, I won't be very careful about which model for infinity categories or homotopy theories I'm working with. I could be working with relative categories and a suitable notion of equivalence of relative categories. Could be working with topologically enriched categories and what are called Dwyer-kam equivalences of topological categories. Could be working with simplically enriched categories and Dwyer-kam equivalences, quasi-categories, and the Joyal's notion of equivalence of quasi-categories, complete Siegel spaces, and with Reszke's notion of equivalences, and so on. All of these things that are written down, it turns out you can promote them to model, they admit model structures. And you can prove that, in fact, these equivalences of homotopy theories actually come from Quillen equivalences of Quillen model categories. So that's a fact that you can prove, which is useful, again, if you want to do any actual calculations. So I'll be suppressing this. I'll be a little cavalier about which model I'm working with, and because the things I'll say will be model independent of models. Okay. So I just want to say what an equivalence of topologically enriched categories is, or simplically enriched categories is, so it doesn't seem all very opaque, so that you know at least what it means for two homotopy theories to be equivalent, in the sense that we're talking about. So a functor F, a topologically enriched functor F, from one topologically enriched category C to a topologically enriched category D, is called a Dwyer-kam equivalence if the following two things hold. For any pair of objects, the induced map on mapping spaces should be a weak equivalence of spaces. So if spaces is topological spaces, then this is a weak homotopy equivalence of topological spaces. If I replace top by simplicial sets, this would be a weak homotopy equivalence of simplicial sets. And second, I want the induced map on homotopy categories on this HC, which is obtained by taking connected components of mapping spaces. The induced functor on HC should be the equivalence of ordinary categories. Now, the first condition here actually implies that the induced functor on HC is fully faithful, because the induced map on pi naught is an isomorphism. So really saying that this is an equivalence of categories is the same as saying that this is essentially surjective on HC. Okay. So this is the notion of equivalence of topologically enriched categories. So this is one model for the homotopy theory of homotopy theories. It's not a good model, but it's a model that works.
Pranav, what does it mean for a functor to be topologically enriched?
It means that, so these are enriched categories. So that means what is a map between enriched categories? It's something that maps objects of C to objects of D. And for every pair of objects, I specify a map of mapping spaces. From mapping space of X, Y, this mapping space to this mapping space. That's the data that defines a topologically enriched.
Oh, okay.
And it has to satisfy the condition that it's, it's compatible with composition of morphisms and so on.
Thanks.
I mean, I could have not even said topologically enriched. I mean, there is no notion of a functor except for an enriched functor. I mean, there is no like a priori, okay, these are concrete categories. So I can sort of extract a set of morphisms by just looking at the underlying set of the mapping space. And then, define a functor to be just a functor of the underlying set, the underlying ordinary categories. But in general, if I have an enriched category, the mapping space is not a set, it's just an object in some other category. So a C-enriched functor is something that maps, that gives a map of objects, and for every pair of objects gives a map of this object to this object. Each of these is now an object in some other category. Was that clear?
Yeah, thank you. Yeah.
Okay, so this is the homotopy. Yeah, okay, so this is what it means to be equivalent for topologically enriched categories, and I think Rekha will tell you, describe a more sophisticated model for infinity categories, which is quasi-categories, or I don't know which model actually Rekha plans to talk about, but where you have a different notion of weak equivalences and so on. Okay, so I guess I don't have that much time left. So this was the background on working homotopically and so on. I just want to now make the comment about algebra versus higher algebra. So you've already seen that if you have an abelian group, you can construct from that a spectrum, HA. Right? So there's a map from abelian groups, which are Z modules, to spectra, which, by the way, you can think of spectra as modules over this thing called S, the sphere spectrum. The sphere spectrum is a ring object in the category of spectra. It has a multiplication, which which I won't write down, or maybe exercise, you can think about it, or I don't know, maybe Samik will talk about it the next talk. So, so this is a ring object in this monoidal category of spectra. So you can look at modules over this. As soon as you have a ring, something that has a rule of multiplication, which means a map from S smash S to S, you can talk about modules over this ring spectrum, S smash S. I don't know how to write this S actually. Sorry. It's easy in LaTeX, but okay, whatever. So you have a ring structure. So this is a ring, and you can look at modules over this. So what we're saying here is that you have a map from Z modules to S modules, and this is actually base change. So there's a map from S, the sphere, to HZ, and you're just pulling back, you're just doing base change, right? So in algebra, we learn how to base change along a morphism of rings. I can restrict, if I have a morphism from a ring A to a ring B, I can restrict a B module to an A module. Similarly, I can restrict an HZ module to an S module, and that's what this is essentially. This construction which takes abelian groups to spectra, if you like. More generally, you can take chain complexes of Z modules to a spectrum, to a S module. Right? So spectra is nothing but S modules. So in this sense, in ordinary algebra, Z is the initial ring, and Z maps to everything else. And when you say ring, you can talk about K algebras. You fix a ring K, and you can talk about K algebras. But when we don't specify K, we just talk about rings, and that just means Z algebras, things that are defined over Z. If you're a homotopy theorist, then your base ring is S. S is the universal ring which maps to everything else in spectra. And so you can talk about modules over, if I just talk about a ring, I could mean a ring over S, right? Homotopy theoretically. And every ordinary ring, which is a Z algebra, will give me an S algebra by restriction. And similarly, modules will restrict and so on. Modules over Z restrict to modules over S. And modules over an A algebra will restrict to. So the point is that by working homotopy theoretically, we are sort of allowing a more fundamental or deeper object to be the initial ring. Instead of Z, we replace it by S. And the whole of algebra can be pulled back and viewed as sitting inside higher algebra, which is the algebra in the category of ring spectra. So I'll often suppress H from the notation. I'll just talk about algebras. If you like homotopy theoretic stuff, ring spectra and so on, you can think of it as just being an algebra in spectra most of the time. I'll be careful if I need to have more conditions. And if you prefer to work with just pure algebras defined over Z, you can also just work with algebras over Z. But a lot of stuff that I'll say in future lectures will work for ring spectra and rings that are defined over S and not defined over Z. Okay? And not necessarily defined over Z. Not every S algebra is a Z algebra. So not every S algebra comes from a Z algebra. Okay.
I guess S itself is an example.
Yeah, S itself is the universal example in some sense. So yeah. So yeah, I should say I'm sorry. This is all for I think many of the experts in the audience. This will be really basic, but I just wanted to talk about what have I done here? I've mixed up some. I moved some slide by mistake. Let me just move this over. Oops. I've done something to my slides. Just a moment. Oh, I think I moved the slide accidentally. Okay, maybe I'll fix that later. For now, I'll just go to, I'll fix it when I submit the notes. Okay, so I don't have much time. So that's just a comment about higher algebra versus ordinary algebra. So I guess how many minutes do I have? How much time do I have, Surijit?
You have 4 minutes, but you start late, I guess. So you had around 8 or 9 minutes.
Okay, I'll actually try to wrap up. Yeah, in not much more than 4. Yeah, okay, in 4 or 5 minutes then, because I think that would be better to just continue next time since it's a logical breaking point. Okay, so let me go to slide 10. Move over here. Okay. Fine. So that was a general comment. So I won't specify H. Okay. So now just some notation maybe. I think this would be good to fix. So just some notation that I won't have to specify next time then. So if R is a ring spectrum, so ring object and spectra, then I will write mod R is R module spectra. And mod R with the natural notion of weak equivalences is a homotopy theory. So I can work with many ways of talking about this. I could directly work with some infinity categorical model like quasi-categories, or I could just say it's a relative category where I choose some model structure on R module spectra, for example. Okay, I think maybe that would be the closest to the other lectures. So I'm just writing this. You can take define a model structure on R module spectra, and it'll have some notion of weak equivalences, and the weak equivalences are just equivalences of underlying spectra. Okay, and so what is an R module spectrum? It's just a spectrum M and a map R smash M to M, satisfying all the usual associativity constraints, etc. Oh, sorry, usual constraints. Okay, so that's one thing about notation. Now, if R is an ordinary ring or a DG ring, this is just to connect with stuff that Shrikant has been talking about, and Suresh also. So if R is an ordinary ring or DG ring, then I'll write mod R for the infinity category or homotopy theory of R modules, by which I mean the following. So mod R, objects of mod R, will be chain complexes of R modules, and weak equivalences is equal to the set of quasi-isomorphisms. And so in particular, the homotopy category, H of mod R, is what you would call the derived category of R. Okay. And inside this, you have the small objects, which Shrikant defined, mod R small. These are small, compact / small objects, which is, in Shrikant's notation, it was thick of R. And another notation for it is perf of R. So I forgot if Shrikant, did you have retracts in your definition? You included retracts, right? I don't put
Yes. Otherwise, you don't get projectives. Yes.
Right. So then it is the same as what I'm talking about. And here also you can define mod R omega. These are compact spectra. And as I said, every ordinary ring or DG ring, I can view it as a ring spectrum. So I mean, these are, the left-hand side is really a more general thing than the right-hand side. Okay, so I can talk about that. It's just notation. So when I say mod R, I mean this. And another comment, which I think will be useful, which I'll talk much more about next time, is that in the world of, in higher algebra, so in ordinary algebra, you just have commutative and associative and nothing in between. You have associative algebras, and then you have commutative algebras. So what is commutative? Commutative means that xy is equal to yx for all xy, right? But that's a very bad notion, because I told you equality is a bad notion. Homotopy theorists won't like to declare xy to be equal to yx. So if I'm a homotopy theorist, well, if I have an ordinary algebra, the underlying, I can talk about only associative algebra A or commutative algebra A. The underlying set of A is just a set. So there's no notion of paths in that set except the constant paths. So the only notion of equality is just the constant path. So this is fine. But if I'm in higher algebra, you have associative algebras, which you might call also called E1 algebras or A infinity algebras, or A infinity algebras. But then you have a bunch of other things in between. Let me call these like less commutative or more commutative, whatever you want to call them. More commutative. I can draw an arrow here and say more commutative. It's more commutative as you go down. And let me just explain what I mean by more commutative. You have something else. You can talk about E1 algebra, E2 algebras. What does this mean? Well, you see that when I say xy is equal to yx, there could be more than one way of identifying xy with yx if x and y are points in some spectrum, if you like, or some elements, whatever thing. There could be more than one path to identify xy with yx, right? So an E2 algebra is something which just has a choice of an identification of xy with yx, but I don't require all the ways of identifying to be equivalent. Right? I don't require up to the space of choices to be contractible. Right? So if there's some condition I can put on the connectivity of the space of ways of identifying xy with yx very vaguely. I'll give you a more precise definition later on. And you can keep going up En algebras, and then all the way up to E infinity algebras, which are your truly homotopy commutative algebras. Okay, so this will be important in what I want to talk about, that there's a whole hierarchy of commutativity in the homotopy theoretic setting, and that'll actually be very interesting when we talk about duality. Okay, so in the last 2 minutes, let me just say a couple of words, and I'll elaborate on them next time. So examples of duality. So this is what I want to elaborate on next time, and then develop a framework for talking about this. So the first example might be something like Poincaré duality, which is something that you learn about in topology. Second example would be something like Serre duality, which you heard about. So Poincaré duality you heard about in Samik's talk, and he's going to describe it in a more abstract way later on as Atiyah duality. Then you heard about Serre duality in Suresh's talks. And then there's something else we haven't talked about, where there's also local duality, which we'll hear about in Shrikant's talks. And then there's something more algebraic in a certain sense, causal duality. So now I don't have time, so I won't get into explaining what this is, but it's something that you would first learn about in algebra. In words, let me just say, it's like there's a duality between, for example, the exterior algebra and the symmetric algebra on a vector space. I'll make precise what I mean by duality next time. But the representation theories of these two algebras are related in a certain way. And that's an example of causal duality. Another example of causal duality, not of algebras, but at a higher level of operads, is the duality between the two descriptions of rational homotopy theory, as Lie, one in terms of Lie algebras and the other in terms of commutative algebras. So these are all instances of causal duality. So you might ask the question, you have all these different types of duality, and are these different instances of the same thing? For example, are Poincaré duality and Serre duality really the same phenomenon in disguise? And I want to convince you that they are. And in fact, all of the, in certain sense, almost all of these can be put into a common language. And that language requires the use of higher category theory. So I've already given you a glimpse of higher category theory by talking about infinity 1 categories. Later on, we'll need to talk about infinity n categories. And I'll use that to explain, to provide a common framework for some of these dualities. So I think I'll stop there. I'll start the next lecture with the question of what is duality? What do we mean by duality? And can we give a common framework for these examples of dualities?
Thank you, Pranav. So, yeah, there is one comment in the chat box. You can see, yeah.
Isabel duality, a good question. Is that the comment you had in mind? Surajit?
Yeah, no, yeah.
So what is the question actually? So is Isabel duality, yeah, is a duality. So next time I'll talk about, what do we mean by duality? So duality is used in a loose way in many fields to talk about when you have two different descriptions of the same reality, right? So physicists, for example, use it in a very, in a seemingly looser sense. Though if you actually examine what they did, they were like way ahead of us. Like we're, as mathematicians, discovering a lot of the dualities they talked about as instances of things like causal duality, suitably generalized. But how would a physicist, for example, when they talk about duality, they mean that there's two different physical theories, different ways of describing the same physical reality. Mathematics, we often describe we may have two mathematical descriptions of the same underlying structure or entity. For example, Fourier series, right? You have a function, it's just a collection of numbers packaged in a certain way, and you can describe it by describing its Fourier coefficients. It's a dual way to package, another way to package the same data. And you can go back and forth between the two descriptions. Isabel duality is also an example of a similar type. So at the very low level, in this hierarchy of things, dualities are statements about numbers being packaged in a certain way and repackaging them in another way. Fourier series is an example of that. Right? You can repackage a function as a collection of numbers assigned to each point in your space, and the Fourier dual is another collection of numbers and organized in a certain way into a function. And you're asking for, saying that the Fourier dual function captures the same information as the original function. But it turns out that a lot of the times, it's not enough to just work with numbers, but these numbers can be seen as counting something. They can be seen as counting the dimension of some object. And really, you can promote your isomorphism, your duality, to a statement that objects on one side can be identified with objects on the other side. So in other words, you can write an equivalence of categories between two different categories. And if you keep climbing this categorical ladder, you end up with higher categories. And that's roughly where I'm headed. But I don't know if what the question was really about Isabel duality. Maybe I don't know if that answered the question.
Can I? Sorry, Pranav, can I ask something?
Yeah.
Is I don't know if you might have a more general definition than this. By duality, can one expect some kind of higher version of a Morita theory with like examples that you might have given? I feel.
Yeah. So Morita theory would fit into this framework. There is, I think, what I'm going to say is related to what Samik was alluding to. I haven't talked to Samik about this, so I'm not sure. But he's going to talk about dualizable objects in the category of spectra, if I understand correctly, in the symmetric monoidal category. So it turns out that, is that right, Samik? Is Samik there? I don't know.
No, I don't think he's here now.
He's not here. Okay. So in any case, so it turns out dualizable objects are related to the notion of adjoints between functors between categories. Okay. You can talk about functors, and there's notion of adjoints between functors. No, adjoint functors. Sorry, not adjoints between functors. Adjoint functors. And the notion of a dual object in a symmetric monadic category is closely related to the notion of an adjoint to a morphism in a 2 category. And you can extend this to higher level as well. And this is what I want to talk about. I think it's maybe now is not the time because the next speaker probably has to start. But maybe in the discussion, I can tell you a little bit more about what I'll be talking about.
We have lots of things to ask. Yes.